we know how to derive something like x to a constant, right? That was like the first thing we learned how to derive. And x to a constant, when you derive it, is nx to the n minus 1. Mm-hmm. And we know how to derive now a constant to the x. So when you put your variable in the exponent, we know that this derivative is ln of a times a to the x. Figure that out. But we haven't talked about how to derive a variable to a variable. So this is the last thing about exponentials and logs in chapter 5. So to do this, you need something called logarithmic differentiation. Let me show you how that works. Find the derivative of each function. This is 5. So this is the last part. So let's start with this guy here, x to the x. He's fun. First of all, you can't, the derivative of this, right, nobody's going to tell me that the derivative of this is x times x to the x minus 1. Right, you can't just bring down this guy and then subtract 1 from the power. Right, because they're both variables. It does not fit this formula. So when you have a variable base and a variable exponent, the trick is to natural log both sides and do implicit differentiation. So to bring this exponent down, right, because I don't like having an x as a base and an exponent, I'm going to bring him down by taking a log on both sides, naturally. All right, so ln of y, I'm going to leave alone for now. But on this side, I introduce the natural log so I can apply my log rule. My log rule lets me take down any exponent, whether it's a variable or not. My log rule lets me take this down in front. And then I can take the derivative of both sides implicitly. Right, do the derivative with respect to x on both sides. So I introduce a natural log to bring down the exponent, and then I derive. What happens when I derive ln y?
Cancel each other.
Right, so when you do the derivative of natural log, you get 1 over whatever's inside times the derivative of the inside. What happens when you do the derivative of x ln x? Product. Gotta do product. It's a product, right? Times. So the derivative of x is 1 times ln x plus x times the derivative of ln x.
1 over
So here's where I'm at. 1 over y dy dx equals ln of x plus just 1, right? Because x on top, x on top. And the whole point of this was to find dy dx. Find the derivative of each function. The derivative of y is dy dx. So I have to solve for dy dx. How do I do that? Multiply by 1. I know what y equals. Can I plug in for this y?
X to the x.
It's x to the x.
Mm-hmm.
So the derivative of x to the x, just like all exponential functions, has an x to the x factor in it, but then it also has a variable multiplier. ln x plus 1. Whenever you're trying to take the derivative of a variable to a variable, this is the method. So I'll do another one. But so variable to a variable, you hit it with an ln to bring the exponent down. So sine x to the 1 over x. I want the derivative. What do you think?
Mm-hmm.
Because you have a variable in the base and you have a variable in the exponent, you're going to natural log both sides. So you write natural log on both sides. I'll put an ln here, ln here. The whole point of the ln is to help me bring that exponent down.
Mm-hmm.
Then I'm going to take this guy, pull him in. So ln y is equal to 1 over x times ln sine x. And 1. All right, now that I have the exponent down, I can actually take a derivative.
Mm-hmm.
So I hit both sides of dx. Do you want to leave it like this and do the product rule, or do you want to put the x on the bottom and do the quotient rule? You don't go. Product rule. All right, let's do product. We like product rule slightly better. If I were going to do product rule, I would probably change 1 over x to x to the negative 1. So then when I do the derivative on both sides, left side is easy. Derivative of natural log is 1 over whatever's inside times the derivative of the inside. Derivative of the right side, you have to do product rule. So start with the derivative of x to the negative 1. Negative x to the negative 2, yeah, times ln sine x plus x to the negative 1 times. Okay, so how do you do derivative of natural log?
1 over cos.
1 over whatever's inside times the derivative of the inside. 1 over y dy dx equals. So let's see, let's make this negative ln sine x over x squared plus cosine over sine is cotangent. So cotangent x over x. And then to solve for dy dx, I just multiply out my y. So the y will go away here, leaving me with dy dx equals all this garbage multiplier here, negative ln sine x over x squared plus cotangent x over x, but then times what?
Sin x.
1 over x. If you run into a function that has a variable base and a variable exponent, you can derive it. It just takes a lot of effort. So that's 5. That's my spiel about exponentials and logs. You have to know how to do what? Derivatives and integrals of e to the x, right? Derivatives of natural log, and then integrals that have du over u. Those are the main things. If you happen to have a variable base and a variable exponent, when you do the derivative, you have to do this logarithmic differentiation, but that's not the most important thing to me. I'm sure there's some guy out there somewhere who thinks this is super important. Sure. But anything I can clear up before I talk to you about inverse string functions. With all this stuff, you want to be able to do, all the stuff we did in chapter 1, 2, and 3, except with logs and exponentials, right? So for example, if I ask you to find the relative mass, and then we'll do it. If I say something like find all relative extrema of y equals x times e to the 3x. How would you do that? Yeah, so this is combining stuff we did in chapter 3 with stuff we learned in chapter 5. But the main thing to remember is to do relative extrema, what do you need? Derivative equal to 0. Or another way of saying that, critical numbers. Right, you find the critical numbers and then you can do your first derivative test. So don't forget this stuff. How would we calculate the derivative here? Product rule. Right? Derivative of x is 1. Keep the e to the 3x plus x times
E
e to the 3x, right? The derivative of the second function, the derivative of e to the 3x is e to the 3x
times 3.
times 3 because of a chain rule. The derivative of e to the 3x, e to the 3x, but the inside's more complicated than x, so you have a chain. And let's clean this up a little bit. What can I do? Yeah, factor out that e to the 3x, and you get 1 plus 3x. I'm trying to find relative extrema, so I'm going to set this to 0. 0 and I'm defined. But there's no denominator, so I don't have to worry about it. But I can set it equal to 0. Y prime equals 0 tells me that I have two options. Either e to the 3x equals 0, or 1 plus 3x equals 0. right? I just said, if I'm trying to solve a product equals 0, you set each factor to 0. Why is this?
It's always like, there's a,
It's never happens. E to the 3x is never 0. Why not? This is an exponential function, right? You can't take a base to a number and get a negative number. Or you can remember the graph, right? E to the 3x, or the graph of e to the x, looks like this. It approaches 0, but it never hits 0. So this guy doesn't give you any solutions. But this guy will. Yeah, negative 1/3. Now, I'd really like to know if this is a minimum or a maximum. So how do I test to see whether this is a min or max?
that's
First derivative test. All right, do your number line. Negative 1/3. Test something to the left. Oh no, 0 is not to the left. Negative 1/3. Negative 1. Test something to the right. 0. Plug these into the original function. Where do I plug these in to test? The derivative. Okay, good. Don't gotta get mad. So if you put negative 1 into the derivative, this factor is always positive. I don't care what you put in for x, e to the 3x is always positive. If you put negative 1 in here, 1 minus 3, negative. Okay, move to 0. E to the 0 is 1, still positive. If you put 0 in here, this guy becomes positive. So I was going down, then I go up, down, up, meaning this guy is a minimum. A relative min is equal to, the x value is equal to negative 1/3. How would I find the y value?
plug into the original.
Put it back here. So I would put negative 1/3 times e to the 3 times negative 1/3. This is e to the negative 1. Whatever. Negative 1/3 e to the negative 1. Or negative 1 over 3e. Y value x. So not only are you responsible for knowing the derivatives and the integrals of e to the x, and then natural log x and 1 over x, but you want to be able to use all that information with stuff that we learned.